Chapter 7, we're going to be discussing sampling distributions, which will be a foundation for all of the other chapters that we discuss this semester. So there are four main themes of statistics, and we've already covered the first three themes first semester. Now, all of second semester, we are going to be focusing our attention on the fourth main theme, which is inference. Now, you might be wondering, well, what exactly is inference? So inference is when we want to make or test a claim about the population. Now, this population could be anything. These claims could be anything. But for the most part, we are going to focus our attention on proportion questions and mean questions. So for instance, we might ask what percent of voters will vote for candidate A in the next election? Or what is the average life expectancy of U.S. residents? We can use inference to come up with a very good idea, basically a mathematical hypothesis for what the answers are to these questions without actually knowing the true value for these population values. Now, what we're going to focus on a lot this chapter and really throughout the semester is I have full results from the Lincoln, Nebraska National Guard Marathon from May 7th, coincidentally my birthday, not 2006 though. And so the first question that we're going to explore about this marathon is, what is the mean age of marathon runners from this race? So if you had to stop and think, what do I think would be the average age, the mean age of all of the marathon runners from this race? And so if you just had to come up with an educated guess, what do you think would be the mean age of all the runners from that race in 2006? So you can kind of keep that number maybe in the back of your mind, and it'll be something that we'll explore later. Now, the second question we're going to explore from this data set is, what proportion of runners are from the home state of Nebraska? Because it was in Lincoln, Nebraska. So you would think if a race is taking place in Nebraska, there's probably going to be a lot of, locals or people not too far away from Lincoln, Nebraska. So in the back of your mind, just think about, what do you believe would be the answer to this question? What proportion or what percent of runners do you believe are from Nebraska at the Lincoln, Nebraska National Guard Marathon? Now, I could look through all 974 runners' data to answer these two questions. And honestly, I already did. But that would take some time. And it did. It took me a little time to figure out what the answer to those two questions are. And number two, we won't always have access to the population data, which I did have access to. So we must settle for the next best thing. And that's taking a sample. And hopefully a random sample or a simple random sample from the population. Now, is just one random sample really going to answer our questions about the population? Not really, but it's going to give us a really good educated mathematical guess about what the answers will be for our two questions. So since we don't know anything about our population distributions, it's SOCs, right? It's shape, outliers, center, spread. Then we need a distribution that we can rely on. And that's going to be the foundation of this chapter. And that is a sampling distribution. Now, what's so special about a sampling distribution? Well, it's going to give us valuable information. It's SOCs. We're going to be able to figure out what are the shape, outliers, center, and spread for a sampling distribution that we can use to determine whether a claim about the population is plausible or not plausible. So what is a sampling distribution exactly? Well, this is the definition, and we will kind of explore some ideas around what a true sampling distribution is. But to be honest with you, we're never really going to be able to see or come up with the actual true sampling distribution. We're just going to be able to look at little snapshots of it. So the definition is, if we took every possible sample of the same size from the population and graph the statistic of interest from all of those samples into a dot plot or a histogram or any other type of graphical display, then that graph is the sampling distribution. And again, what I mentioned earlier with we're not really going to be able to view the true sampling distribution is because it involves around this idea that if we took every possible sample of the same size from the population, and that number is most of the time going to be an astronomically large number. Now, the main idea for visually what a sampling distribution kind of looks like, and this is just kind of an intro to what it's going to look like, is imagine we have the population, and the population has a mean, and we don't necessarily know what that population mean is, right? Like, what is the true average mean age of all the marathon runners? We don't know what that number is. So we're just going to call it mu. It's going to be a variable for right now. We don't know what it is. But what we could do is take a random sample, hopefully a random sample from our population, and we could calculate what the average age of those marathon runners are. And so that's what each of these little bubbles represents, is a sample taken from our population, and we can calculate the statistic that we are wanting to kind of emulate. We want to figure out the population mean, but if we take a sample, we're going to have a sample mean. So if we took all of these sample means and started to graph them in a dot plot or a histogram or a stem plot, then this is the starting creation of a sampling distribution. Now, some questions that pop up. How many samples can or do we need to take? Because you can see I took a lot of samples from here to make this dot plot. And what sample size do we need? Because I did mention that if we had to take every possible sample of the same size. So do we take samples of size 10 runners, 20 runners, 30 runners, 50, 100? Like what sample size do we need here? So these are a couple questions that we're going to kind of explore as we look at sampling distributions. Now, how many different samples of, let's say I pick 30 as my sample size. How many different samples of 30 runners would we have to gather to cover every possible sample from a population of all 974 runners? How many do you think there would be? Any idea? And I guarantee it's going to be a number so big you probably wouldn't even know how to say this number. And it's not a Google. Google, it's smaller than a Google, so don't worry about that. Or a Googleplex or any of those crazy, like astronomically large numbers. So how many different samples of size 30 could we get from a population of 974 runners? And that answer is this many. Yeah, that many. How many is that? Man, I'm trying to remember. I want to say this was like 1 octodecillion, I think, maybe. I mean, this is like crazy, crazy, crazy big to figure out what 974 combination 30 really would be. So thankfully, we don't need to take every single possible sample of size 30 from a population of 974 runners because that's just way, way too many. We can get by with much, much fewer samples to make a really good educated mathematical guess about our population. Now, there may be only one population distribution, right? There's the shape, the center, and the spread of our, let's say, average age. If we look at the ages, there is one true shape, there's one true center, there's one true spread of the population distribution of ages, but there are as many different sampling distributions as there are people in the population. It all depends on the sample size. So we could have a sampling distribution based on samples of size 2, samples of size 3, samples of size 4, samples of size 30, samples of size 100, samples of size 300, all the way up to samples of size 974, which would literally be everybody, right? So now what we're going to do is explore some patterns that emerge from sampling distributions depending on the sample size taken. And we're specifically going to look at sample sizes of 10 runners, 20 runners, and 30 runners. And you will immediately start to see, as we pull together all of our data from our random samples, the patterns that are going to emerge with the shape, the center, and the spread of our sampling distributions. So we're going to go back to that first question. What is the mean age of marathon runners from this race? So I had my students select some random samples, and first we started with random samples of size 10 runners. And so each student took a random sample of 10 runners, calculated their sample mean age, X bar, and I had those students come up and put their average age up on the board. And that's what each of these dots represents. So for example, I had one student get an average age of their 10 runners was 29 years old. So they had a lot of younger runners in their 10. Versus on the other end, I had 10 runners whose average age was 49, which meant that a lot of those 10 runners were much older than younger. So again, each of these dots represents one student's sample mean age of 10 runners. Now, some things that we will discuss here is predominantly going to focus on the shape, the center, and the spread of these sampling distributions. The other thing I want you to keep in mind is that this is not the full complete sampling distribution, because that would take billions upon billions upon billions of random samples to be able to pull off. And we just don't have the time, energy, or resources to do that many random samples. So this is just a very, very, very small snapshot of what the true actual sampling distribution appears to be. But it gives us kind of a really rough idea of what to expect. So we can start to look at, well, this kind of looks, I don't know, maybe skewed right-ish. Some people might say it's almost developing a bell-shaped curve in there, which I would agree with. But for right now, we'll say maybe it's skewed slightly. Now, where is the center of this sampling distribution at? And I don't know, maybe around 38, 39, 40, somewhere in this vicinity, 38 to 40-ish would be the center, the mean of all of the means, the mean of all the sample means. And then in terms of spread, the easiest thing to be able to look at initially in terms of spread will be the range. So if we were to look at the max and the min, we got a max of 49, we got a minimum of 29. So right now we have a range, a spread of 20 years. So we've got quite a bit of spread in there. Now, after that, I had my students take a random sample of 20 runners instead and calculate their average age, and they each came up and put their data up on the board. And so we start to see a little bit better of a pattern emerge here in terms of shape. This is definitely looking more approximately normal-ish, right? It's not the best looking approximately normal shape, but we got to remember this is a very small amount of data compared to all of the different possible random samples that we could take from our 974 runners, 20 runners at a time. So we're not going to see a beautiful looking normal distribution, but we're starting to see a normal distribution emerge. Where does the center of this sampling distribution appear to be? And I would guess, I don't know, maybe 30, 39 kind of looks right in the middle-ish. Some people might say maybe 38 to 39-ish, somewhere in there. And then in terms of spread, what are we looking at for a range? We got 32 to 44. So we're at 20, no, not 20, 12. So our spread has decreased from 20 for the range to 12 for the range. So we could see the shape starting to emerge more approximately normal. The center looked to be about the same. The spread got smaller. All right, now this is one that I've collected data from many students over the years. And so this is going to be a better indication about what that sampling distribution is really going to look like in terms of its shape, its center, and its spread. And so for this one, we can really see the shape. We get this almost very nice, beautiful looking, approximately normal shape. But again, there's some rough edges here and there. But again, this is just a very, very tiny snapshot of what the actual true sampling distribution looks like. but we can see that normal shape emerging. Where does the center of this distribution appear to be? And I would think maybe around 39. Again, we could probably be 39, 38-ish. Some people might lean more towards 39 to 40-ish, somewhere in there. But I would think in general, 39 looks like kind of a good number. And so the patterns that we saw happen, the patterns with the shape, the pattern with the centers, the pattern with the spreads from those three sampling distributions, as we increased our sample sizes from 10 runners to 20 runners to 30 runners, the shape became more and more normal looking. And again, it wasn't perfectly normal looking, but we could start to definitely see a more normal shape emerging from 10 to 20 to 30. In terms of the center, it stayed about the same, honestly, from all three sampling distributions. And it was around, if I had to give one number as a guess, 39 seemed like a pretty consistent number that would have been. And then what happened in terms of the spread? Well, it kept getting smaller and smaller and smaller. And I think I left out my range on that last one. So 33 to 44, the range was 11. So it didn't get that much smaller than what we had seen for the 20, because the 20, it was 12. And then for the 30, it was 11. So we see it still got smaller, but maybe it wasn't as big of a jump as it was from 10 to 20. So more normal looking, the center stays about the same every time, and our spread, our variability gets smaller and smaller and smaller. So if I had to give my best mathematical guess about what do I believe is the mean age of all of the marathon runners, well, I guess I would use the center of those sampling distributions, the average of the averages. What is the mean of all of the sample means that we were seeing there? And so my guess would be, 39 seemed like a really good mathematical guess. And now the actual answer is 38.81, which is really close to what? 39 years old. So that's the amazing thing that we see with sampling distributions is we didn't know anything about the truth about all of the ages of all of the marathon runners, but I'm now sharing that information with you. But we didn't know anything about what the shape of the population looked like. We didn't know what the center of the population looked like. We didn't know what the spread looked like. But just by taking small random samples, and this is the kind of thing that kind of blows my mind, is even if we looked at the random sample size of 30 back here, we got to consider we were taking sample sizes of 30 and the population size was 974. I mean, this is still a very small percentage of the population. And so even though we only had 30 runners, those 30 runners average was really kind of zeroing in on that 39 years old for the population mean. So again, that kind of just boggles my mind how such a very small amount of information from the population can actually lead us to some very good mathematical guesses for what's true about the whole population. Now, question number 2. What is the proportion or the percentage of runners that are from Nebraska? And so again, I had students take samples of size 10, 20, and 30 so that we could kind of see some patterns emerge and discover maybe which sample size is best, or small sample size is better, or bigger sample size is better. And so for 10 runners, everybody had a nice multiple of 10 because, out of 10, you're going to get a number that's a multiple of 10%. So I had some students maybe only get 1 out of 10 of their runners were from Nebraska. And then I had some get 7 out of 10. But for the most part, most of my students were around 3, 4, or 5. Now, in terms of shape, what kind of shape do we see here? Well, I'm kinda-ish seeing a normal shape maybe emerging from our data. I could see some people saying, well, it kind of looks skewed left. And I would agree this looks skewed left. But if we were to take more and more and more samples, we'd probably start to see that approximately normal shape really emerging. What about the center? The center is maybe, and again, we can only give multiples of 10s as our real good estimates here, but it's looking like somewhere in this 40 to 50% range. Some people might say maybe it's 40%, some people might think 50, But really, those look like they're taking up too much of the distribution. So I would guess somewhere between 40 and 50% is maybe the center. And then again, in terms of spread, the easiest thing to look at for now would just be the range. And so we got a range of 60%. Now, for 20 runners, now we really start to see from our data, there's this more normal looking shape starting to emerge. And again, it's not perfect, but it's definitely looking more normal than it was before. In terms of center is looking pretty good, maybe 45-ish, maybe somewhere between 45 and 50% is the center. 45 is looking pretty good, I think. In terms of spread, 25 to 70% would be, 45% for a range? So we got smaller. We were at 60%. Now we're at 45% for the range. So we see the same pattern for the mean sampling distributions as we do for the proportion sampling distributions, where the spread seems to be getting smaller and smaller and smaller. And then let's look at the 30. And so again, we kind of see now starting to emerge. Definitely a more normal looking shape. It's rough around the edges, but I'm starting to see that bell-shaped curve emerge. Where's the center of this sampling distribution? Again, it's looking around 45-ish, 45 to 50-ish maybe, somewhere in that area. Spread, we got 30% to 65%. So we got a range of 35. So it got slightly smaller. But again, consistently, we saw that the spread got smaller and smaller and smaller. So what happened to the shape? Just like for the mean sampling distributions, it became more and more normal looking. What happened in terms of the center? It stayed about the same, honestly. It was around maybe that 45-ish% number. Some people might go, I'm going to guess 47%, 48%, and that's fine. We really only had the best estimates we had were 5% increments. So if I had to give my best guess to the nearest 5%, I would have said maybe 45%. Some of you might have said 50. Maybe some of you would have said 40. But if we're around 40, 45, 50, why not shoot for the middle and go for 45? In terms of the spread, we saw the range was decreasing each and every time. It wasn't as big of a decrease from 20 to 30 as it was from 10 to 20, and that'll happen. So as our sample sizes get bigger, we'll notice that small decrease happening with our spread, with our variability. So if we had to give our best mathematical guess, what do we believe is the proportion, the percentage of runners that were from Nebraska? And so again, if I had to guess, I would go for that center. I would go for the average of the averages here. And so I would guess around 45%. And so what is the actual truth, Steve Harvey? 44.56%. That's really darn close to 45%. So again, this kind of astounds me mathematically that we can take these very small sample sizes from a pretty large population, and just from those small sample sizes, when we look at them collectively together as a sampling distribution, it starts to reveal some really good mathematical possibilities about the truth for the population. And there is a main reason why we looked at a mean problem and a proportion problem, and those reasons will fall into the next video. So until then,